So, oops, sorry. Yeah. So, hello everyone. Thank you for joining us for the final session. Today, we have a speaker, the only speaker from the last WCNTDA in 2019. Paul was here in Malaysia, and I think he enjoyed the food a whole lot, more than the company. I don't know. Let's ask him. And we were together doing our PhD in Imperial College. Before that, he did his degree and master's in Geneva, if I'm not mistaken, and a double master's too in Geneva, one in physics and one in statistics, I think. So he is very well equipped to talk about many tools of data analysis. And with great respect, I invite Paul to start sharing.
Yes, hi Fatima, hi everybody. Thank you for the very nice introduction. So let me just... Yes, can you see my screen now?
Yes.
Okay, good. Yes, all right. So yes, so thank you for inviting me again. As you said, like I was there 2 years ago now, which seems like ages ago, and I did enjoy the food very much. That's true, but I also enjoyed the company very much, and much more than the food actually. Even though the food was really nice, so that's saying something about the company, I guess. So yes, so I start. I'll be probably it's going to be a bit shorter than 2 hours, which you probably won't mind because I think for you it's already quite late. And yes, so if you have questions, just raise your hand. And so unfortunately, I only have one screen at the moment, so I cannot see both Teams and what I'm presenting. So Fatima, could I ask you to facilitate the questions?
Yes.
And
Yes, indeed, I will. And they will be waiting eagerly for the one question in which we have a prize for it as well, Paul.
Oh, yes.
That one too. So, all right. I will look out for comments and things.
Okay, that's great. So, so now I'm going to start. So, so as Fatima said, so I did a bit of statistics back in the days when I was a student, but that wasn't really with the aim of doing research, but rather as a backup plan if I needed to go to the industry. So at the time I didn't pay that much attention, but since then, again, I went into networks and complex systems, and more the notion of big data analysis became intertwined with, of course, statistical learning as it was before, but also complex networks and representation of complex system and the analysis of these networks afterwards. So the session of this WCNTDA is dedicated to clustering, and so and this session will be particularly about clustering in complex networks using a tool that's called Modularity, and we'll see that's only one of the methods that is used to detect clusters in complex networks, but that's probably one of the most popular. So there's going to be essentially like 3 main parts of an equal length in my talk. So first, I'm just going to go over a bit of what is clustering, like defining a few terms and synonyms, and also explain a bit the rationale, or at least where I'm coming from. So that might be, you might have heard all that story time and again in the past 2 days. So if you have other things to do, then maybe that's a good time to take a break. But then I'm gonna go on and introduce the notion of complex networks and what they really are, and what they're used for, or at least one of their use, and in particular with the angle of trying to say why they're different from graphs. And finally, and that's going to be the biggest chunk of the talk today, I'm going to talk about clustering in complex networks. So I don't have a very original definition of what clustering is, but the main idea of clustering is to group and put together elements of a set, of a system, of a data set that are similar together, and put elements that are dissimilar in different groups, right? So you put elements in different groups, and you want essentially to minimize the difference between the elements in each group and maximize the difference of elements between groups. And yes, and that is a very, of course, very broad task, and there's literally dozens of ways of going around it. And clustering is one of the big topics, of course, in AI and statistical learning methods, AI being understood not just as the sort of initial aim of AI, which was to create like an intelligence, let's say, or something that looked like an intelligent being, but rather any algorithmic method that is here to help humans make decisions. I think that's more or less what AI is at the moment. I mean, of course, it's going to depend on who you're talking to, but I think at least with the people I talk about AI around me, that's sort of the consensus at the moment. That AI is essentially an umbrella term that characterize all method that helps human make decisions in one way or another. And clustering also, one quick remark is, of course, that clustering is often understood as putting elements in sets, right? So you're an element can only belong to one group, and that is, of course, hard clustering, and that's what most people are interested in. But there's, of course, other ways of cluster elements, like for example, overlapping clustering. I talk about that a little bit later, and fuzzy clustering. So not everything has to be like hard clustering. And clustering is, of course, very important, because it's one of the basic tasks that us human and in general probably living beings have to do, right? I mean, even just to group elements in two groups which are life endangering and good, right? So you want to be able to recognize what is dangerous for your life and get away from it, and stay close to what is good for you. So, and when you start looking at the way humans make decisions, then clusterings and classification into groups become like a huge part, or at least a paradigm into which you can explain, or at least understand many things. So it is very ingrained in ourselves. So it's a very logical task for us to ask a machine to help us with. So there's essentially three keywords in that sort of very loose definition that I gave of what is clustering. There's the task itself, which is grouping. And the natural question is, how are you going to group elements? So that's going to be the algorithmic part of it. There's the elements that you want to group, so the data points, let's call them that way. So what they are. So what is it you want to cluster and group? And of course, there's the notion of similarity that I mentioned before, which is, how do you define similarity between two elements? And the notion that goes with it is, of course, how do you define dissimilarity? And sorry, in my mind, these three aspects are not independent, right? So you have the overarching questions that you have, so your research question. But then the methods that you're going to use, so how you're going to cluster the elements, is going to be linked to what these elements are and what is the question you're asking about these elements. And it's also going to be related to the type of metrics you have at hand. So because not all methods can have any input, like all inputs, right? I mean, certain methods like you are going to use a metric, others are going to use filters like mapper, for example. So there can be like a whole set of questions that you need to ask. So it's almost like a decision tree. So which method is combined with what type of metrics, which is fit to answer the question. So it's all a bit abstract at the moment, but I'll go back to this type of schematic at the end when you'll know a bit more about clustering in networks, and I'll tell you about how to design your research, essentially, when you want to cluster nodes in networks. So, yeah, so these are just some of the some more keywords that go with clustering. So there's a tons of methods that you can use, right? And when I mean features, I see essentially because you need to be able to define a metric that characterizes distance, similarity or distance between elements, then you need at least one feature or one characterization, one way to characterize the elements that you want to be to cluster that is non-uniform, right? Because otherwise, essentially, you need a way to differentiate them. And feature is, of course, the words that everybody is using at the moment because it's the dominating words in machine learning. And the metrics that you're going to use to determine how elements are similar, there's of course like tons of them, like you can use correlation, distance, similarity coefficient. And when I say distance, I'm thinking, for example, about hierarchical clustering and all sort of methods. Now there's also something to keep in, a few things to keep in mind when you're doing clustering is that there's a whole range of methods that go from completely unsupervised, which is the type of methods we're going to look at today, towards supervised method, which is more like machine learning, neural networks type of thing, which some people sort of differentiate by calling unsupervised methods clustering or community detection or other synonyms that escape me at the moment, towards classification, which is essentially a supervised task where you already know at least part of the ground truth of the elements that you want to cluster, which is which group they should belong to. Like you have a set of elements of which you know these belong to these groups, so you predefine the groups before. And this also differentiates a bit the unsupervised method, which are more geared towards almost data exploration. So they could be seen as what you would do, like if you think in the traditional statistical analysis pipeline, what you would do at the beginning when you look at statistics of your samples, for example, like the distributions of the features of your samples and also things like unsupervised clustering could be seen as part of that method versus classification, which is a much more operational approach where you know what you want to cluster. You don't know how it's going to happen, the clustering, but you know exactly what you want to cluster and into what, how many groups you want to cluster your data. There's also this notion that there's no unique solution, right? So different methods are going to give, even on the same data set using the same features, for example, they're going to give different solutions, right? And that's true for anything from supervised to unsupervised methods, right? Because even within method, like if you if you think there's, for example, some stochasticity in the way the method operates, or if there is a range of parameters that you can tune in your methods, or even if you use the canonical train tests train like k-fold validation, for example, in machine learning or neural nets, then you're going to have this thing that the results are going to depend on methods and on the data. So there's no unique solution. And as I said, the unsupervised method that we're going to use, we're going to be studying today, are often seen as pure data exploration, so not having real discovery or statistical power in them into saying like these are genuine features in the network. But we're going to see that it's only partially true, and also even if you only use them at the sort of discovery level, you can still then turn the outcome of your clustering as features for further modeling, whether you go for machine learning or more traditional regression models. These are all elements that you can then reuse in your modeling. Okay, so now that concludes the first part about the definition of clustering and what I mean by clustering. So if you have any question, now would be a good moment. And also I'm going to essentially use interchangeably different words. So clustering for me is going to be completely synonymous with community detection, which I'm going to use a lot today, probably more than clustering, because that's the lingo of complex networks researchers or scientists. And also a module is equivalent to a cluster, which is equivalent to a community, which is a group. So these are all equivalent words for me, like today.
Paul, there is no question from the audience yet, but I have a question. So just because we've been talking about clustering for the previous two sessions, so do you have on top of your head an example of an unsupervised learning, the most normal one, and a supervised learning, like maybe the most common one, just to give some illustration?
Yes, so I mean, unsupervised, I'm going to give like essentially everything I'm going to say from now is going to be unsupervised. So that's going to be probably a good example. But the essential notion in the unsupervised methods we're going to see today is that you don't specify anything. I mean, you of course you need to specify a target function, as we're going to see, but then you're essentially specifying as little as possible in what you want in your outcome. So you don't specify how many groups you want to cluster your elements in. You have as few as possible like parameters to tune. So it's really a sort of bottom-up approach. So you have data, you have a target function, and you try to fit this target function to the data. So I think support vector machines, for example, I think would qualify as unsupervised methods. Also, no, that's only partly true, right? Because the basic version of support vector machines essentially make a bipartition of your system, right? So you only find two clusters. But if you generalize support vector machines, as I think it's been done, then you have a situation where you don't specify the number of clusters. K-means clustering, for example, would be something that is a bit more supervised, right? Because although you're not saying anything to your algorithm, so you're not using any notion of ground truth, which I think is really the the criterion that tells apart unsupervised from semi/supervised methods, semi-supervised and supervised methods, is that you don't know anything about the ground truth. So you don't have any a priori notion of what should be in each group. You might tell the algorithm how many groups you want, like k-means, which means that you have some sort of idea of how many groups you have, and therefore you might have some idea of what they should be, but you're not explicitly telling your algorithm which elements should be, or what part of, like what is the, what some of your elements belongs to in terms of groups. And then you have all the, so for example, all the neural networks approach, so are completely supervised, or at least much more on the supervised end of the spectrum, because when you train your neural nets, then you need to have a subset of elements for which you know the ground truth, so which group you want them to belong to, and then you use that to then train your network to classify them properly, correctly in the different groups. So in that sense, it's not really clustering anymore, but it's really classification, which you could see as sort of second step, right? Because you could use unsupervised methods as exploratory methods, then determine the number of classes, and by analyzing the clusters and the elements in the clusters you find, determine which, like, find the ground truth, and then use that ground truth to train a classifier, for example.
Thanks, Paul. So basically, what I understood is that k-means is somewhat supervised.
Yes.
Okay. So
Yeah.
there's like a spectrum, right?
Yeah, there's a spectrum, and I think depending to whom you're talking to, that they're gonna have different boundaries between, like, unsupervised, semi-supervised, and supervised, right? So I don't think there's a hard classification, if you want, sort of fuzzy classifications, and yes, and then there's for example, there's a recently, I mean, a few years ago now, there's been a new class of neural networks that have been introduced, which is graph convolutional neural network. So, which essentially generalizes convolutional neural networks to dataset that have a graph structure, and then you leverage on the graph structure to classify the elements of your data set. And this is said to be semi-supervised because you're essentially using a priori knowledge, which is the structure of the network, to then do a supervised classification task, which is then very like the training part of the neural network approach.
Okay, so convolutional neural network is a semi-supervised, and some of the information comes from the network structure, essentially.
Yeah, so graph convolutional neural networks.
Oh, sorry. Yeah, graph convolutional
neural network would be purely supervised, I think.
I see. Okay. All right. Very interesting, Paul. Paul, is there any chance you can make your voice a bit louder? I don't know if for everyone else, but for me, you sound slightly far away.
Okay. Okay, I'll try. I mean, yeah, I don't think I've changed anything in my setup, so. Okay, I'll try to speak louder then. Sorry.
No, maybe it's just me. Nobody else is complaining. So, all right. Maybe you can put in comment if you think you can't hear the voice, but otherwise, I think it's okay. Okay, so do continue, Paul. Thank you. And oh, by the way, they haven't had any complex network background yet, so this is the first time Okay, Dr. Siti Nur Rafida can hear clearly. That's good. All right.
What? Sorry, I didn't get. I didn't catch the last part.
There's a participant said that she can hear you clearly, so that's good.
Okay, so yes, so I suspected that not everybody might be familiar with complex networks. So I'm going to give you a 5-slide crash course on complex networks, and essentially trying to give you the sort of basic vocabulary that you're going to need to survive the next hour. So underlying complex networks is the notion of graph, right? And the graph is a mathematical object that is defined as a set of nodes that is connected by a set of edges. And for example, here on that cartoon picture of a network, of a graph, the nodes are the round stuff which are in blue, and then they're connected by edges. Right. Some people call the nodes vertices and the edges links, and they mix and match. So I think nodes and links, the usual pairing is node and links and vertices and edges, but I tend to use nodes and edges for, I don't know why, but that's just how because probably these are my two favorite words in the two subsets. But anyway, so graphs have been studied in pure math in their own right and trying to understand structure. So it's also linked to knot theory and all sort of things. So there's questions about invariance and coloring problems and structure of the graph itself and classes of graphs. But as you probably know, a lot of objects in our everyday lives now are even calling themselves social networks or networks, which is essentially saying like it's a social graph, like Facebook, Twitter, LinkedIn, you name it. There's tons of examples. So a complex network is essentially a graph, but with something more. And again, there's no sort of clear definition of what a complex network is, and or rather how different it is from a graph. But I tend more and more to say that you need something more than just topological information to call that a complex network. And it comes from the fact that you can have attributes or features associated with the nodes and with the edges. So you can have different types of nodes, or they can have different types of importance measured by something that is not topological, so that is not directly related to the graph structure. You can have different types of edges, or you can have weights on the edges which indicate the strengths of interactions or similarity between the nodes. And this sort of naturally follows from how complex network came about, right? Because, so as I said, you had graph theory at the beginning, and then social scientists, probably in the 50s, 60s, they started drawing social networks, right? Which they would like go somewhere and interview people, and then ask, so who are you friend with, and what type of relationship do you have with that person? Is that like a friendship? Is that professional? Is that, I don't know. And that would be a social network. So that would still be a graph, but it represents something. It's not just an abstract construction. And as the data set that you could access got bigger and larger using computers, essentially, and that you could sort of, for example, like crawl the internet to find, like Google, for example, is a network, essentially. Like the Google algorithm is essentially a random walk, or a biased random walk, rather, on the World Wide Web, right? And it uses different notions to rank pages and class them. So this is essentially a complex network and a complex system, right? And yeah, and complex systems can are naturally represented as complex networks many of the time. So I won't go into a big discussion about what complex systems are, because that would take probably just another hour just by itself. But you can think of complex systems as large systems with units that interact, and by the interaction they create something. So there's this usual saying that is attributed to Plato, I think, which the whole is more than the sum of its parts. So these sort of ideas are at the center of what a complex system is. And of course, because complex systems are interacting agents, then a complex network is a natural way of representing complex systems. So there's a class of complex systems that you can directly, for which you can directly measure the connectivity, right? And the connectivity meaning how the elements are connected together. So for example, you have social networks, right? Facebook, Twitter, you can just crawl Twitter and you're going to know who's following whom. You have also, for example, like that's the bottom left picture of the US is the air traffic network. So each node is an airport, and then the links and then there's a link whether these two airports are connected by flight, and the weight or the thickness of the edges is proportional to the number of flights. Right? And of course, you have the structure of the human brain, right? So the structural network, not the functional network. So really, literally, how brain regions are connected by white matter tracks. This is something you can actually measure. And so direct measurement is one way of obtaining complex networks. And you can also use similarity measure. And that's where we sort of start overlapping with what I discussed before about clustering, is that being connected, for two nodes being connected, can mean they share some level of similarity. For example, you can think again of the brain. So that's the left, that colorful picture on the right side of the slide, where instead of measuring the physical connections, so the white matter connection between regions, the brain activity over time of these regions is recorded. So you have a time series, and then you measure the similarity of the time series for every pair of brain regions. So that gives you a functional network, or a complex network, that represents the functional connectivity of the brain, which is in general different from the structural connectivity. And you can see that this functional brain is colored in like 6 or 7 different colors, and each of these colors represent clusters of stronger similarity, of region of stronger or higher similarity. So this is like the first example of network clustering that's I mentioned today. And interestingly, when thinking about complex networks and complex systems in general, the notion of modules or cluster or community is like comes up very naturally. And because complex networks are a representation of a complex system, it should at least mirrors not all its properties, but that's at least some of its key properties. And the modular structure, and particularly like hierarchical modular structure, is a hallmark of complex systems. And there's this very nice paper by Simon, who later on went on to win the Nobel Prize in economics. It's a really nice paper. So he didn't win the economic prize, the Nobel Prize for that paper, but it's a really nice paper, and also it's published in the Philosophical Transaction. So it's a philosophy paper with some quotes. It's actually very readable, and it really explains well, or lays the basis or the foundation for the reason modular structure emerges in complex systems. And I won't go into the details of it, but essentially there's this notion that it creates more efficient, resilient, and effective systems, right? And just to give you an idea of what a hierarchical model structure is, so you could think of the picture on the right-hand side describing a school system, right? So the brightest red, so the smallest nodes would be the original nodes of the system, and they could be classes of a given degree, right? So then, of course, students of the same age are going to be more closely related or more likely to be friends together than they are with children with or humans of a different age. So the core element is the classroom, and then you can see modules of classroom of the same degree and same age merging within a school, which is the blue community essentially. And because it's more likely that you know somebody from the same school than you know somebody from another school on the other side of the city, for example, you live in. So you have this natural hierarchical modular structure in social relationships, right? And interestingly, that holds up and that comes up in all sort of settings, which both humans and technology and not humans, but just nature in general. It's a very common representation of nature. And yeah, so that was it actually for my crash course on complex networks. So I tried to give you some basic vocabulary so you can follow the rest, and also give you a sort of justification as to why these are important and interesting objects to consider, particularly now that we have access to a lot of data about everything. So it's very natural to try to find some structure in the data, some network structure in that data, because of course, as we're going to see, that topology, what that structure does is essentially it filters out part of the information about your original system. So it's already guiding how clustering is going to happen. So if you have any questions about complex networks, that would be a good time to ask.
No question. Not I can see, but I guess are you going to explain that clustering is?
Sorry?
Are you clustering? You are going to use the word community detection, right? To interchangeably to refer
Yes.
to clustering, right?
Yeah, clustering,
Yeah.
community detection, module, community, groups are all equivalent. I try to be consistent, but I think I failed. So
yeah. I have the same problem. So maybe I can just repeat everything. That a network and a graph will be used interchangeably, and nodes and vertices are also the same thing. Edges and links also maybe be used interchangeably. So in we have sometimes this problem that we will use different words for the same thing. And then clustering and community detection will be used interchangeably. Communities, modules will be used interchangeably with clusters, right?
yes, so just to go back to the graph networks and node versus links edges. So I was just pointing out that in the literature in general, like these are synonyms, but me, I always use complex network and nodes and edges. So that should be consistent throughout.
Okay.
The bit where I
Good for you.
go back and forth sometimes is clustering and community detection. clustering. I tend not to use clustering very often, but because that was the general title of the meeting, then I thought I might use both.
Yeah, but no problem, Paul. You can just use community detection. But just I'm sure people will already understand that community detection is a type of clustering. Okay, thank you. So you may continue, please.
Okay, so the aim of clustering in complex networks then is to group nodes that are similar, right? And interestingly, of course, we're going to rely a lot on the structure of the network to be able to cluster and find criterion to cluster nodes into modules. And interestingly, structure is not just another feature in the sense that you can measure, let's say you can measure 10 attributes for each node. And parallel to that, you can measure the structure of the network that connects the nodes. Then structure is not just another feature because it's not just a local information about a node, right? It's the connectivity, the general connectivity patterns of the nodes. So the network is a global property of the data set. So in that sense, it's not just a nodal feature. It's a system-wide feature that helps you locally to understand the shape of the data or the shape of the space the data comes from. Right. There's of course connection with that I won't go into today, but with topological data analysis. And I mean, I think many people could see like networks theory as part of topological data analysis, and the notion of the shape of the space, the data, so the nodes you're looking at is living on, and there's a whole discrete differential geometry approach to complex networks where you can define curvatures and all sort of things. But I won't go into that. Sorry, I was digressing. So yes, so remember that structure, even if you derive the structure as I mentioned later, that sorry, so you could start with no network, so not measure any network, as I said, and measure the similarity of some attributes of the nodes to create that network. So, and the interesting thing is that even if you use this purely local structure to measure the connectivity, you still end up with a global indicator of about your system. And of course, as in any clustering task, you want to group nodes that are similar. And interestingly, I think, of course, I laid out the nodes such that it should be obvious, but I think if I asked, and I should have asked before turning the slide, but if I show you that graph, try to forget that I flicked the slide, what would be a natural partition of that graph, right? And I think many people would sort of intuitively say like that there's a cluster of blue nodes, there's a smaller cluster of pink nodes, and there's a cluster of turquoise nodes or cyan nodes. And that is interesting, right? Because sort of instinctively we have a notion of what should constitute a cluster of nodes, right? And there's this notion that because cluster should group nodes that are similar, then you instinctively associate connectivity with similarity. So regions of the network that are more densely connected should or could be considered as clusters, while when they're loosely connected together, then this should like provide boundaries between clusters. And now the task that we have is to try to systematize that and formalize it as much as we can. So underlying this is the notion of the minimum cut problem. So the minimum cutoff graph is a partition of graph into, like in this in this very simple example, where you want to group the nodes in your system into two groups, two disconnected groups, and to disconnect the nodes, so to create two sub-networks that are independent of each other, then you want to minimize the number of edges that you need to cut. Right? And just to give you a definition of what a partition is, so what I will call a partition, and I will use that word a lot, is, so a partition is a clustering. So it's a set of clusters that define a clustering of your system. Right? So here you want to create a partition of a graph into two communities, two clusters. And you want to do so by cutting as few edges as possible. So, of course, if you cut the middle edge, then just by cutting one edge, you end up with two disconnected subgraphs. So you have one triangle graph here with the blue nodes, and one triangle graph with the pink nodes. And of course, yeah, sorry, that actually is slightly wrong. So I have to correct that before sending you the slides. So of course, it's not the number of edges between communities that you want to minimize, because once you cut them, they're not present anymore. But you want to minimize the number of edges that you're cutting to define your two communities. So the min cut problem. So the min cut problem in such a simple graph is very easy because you can do it by hand. But when you have larger networks and when you relax the constraint that you want two subsets, then it becomes a combinatorial problem. And as most combinatorial problem, it becomes NP-hard, and you cannot really do anything with it. And also, there's something that you're not controlling for, right? So essentially, the argument here is that a solution to the min cut problem is not necessarily going to give you a good partition of a node of a network, right? Because the only thing that the min cut tells you is that you should minimize the inter-community edges, but it doesn't tell you anything about the communities themselves, right? And just relying on the number of edges that you're cutting to divide your network is not really telling you anything about what remains. So to the communities themselves. And Newman, which I refer to in the next slides, sort of introduced this notion that you don't just want to minimize the number of edges you want to cut, but you also want the notion that the edges that remain are more, or this notion of expected edges. So you want, because you want the modules to be more connected than, you want more connectivity within modules than between modules. And what Newman argued is that if you only look at the min cut problem, then you're not controlling for that at all. You're just controlling for cutting as few edges as possible. And so you don't have this global constraint of considering the structure of each modules, the connectivity of each module. So what he proposed is modularity, which can be formulated in a 52 equivalent way, which is you want the connectivity within communities, so the observed number of edges within community to be larger than the expected number of edges in that community, right? So the key to modularity is going to be what you mean by expected, right? But you want to group nodes together that are more connected than expected, than average, if you want, which goes back to this notion of similarity. So you want nodes that share more together than they share with other nodes. And alternatively, you can also rephrase that with using the edges between communities. So you want the edges between community to be fewer than the expected number of such edges. And so modularity was formulated like in the early 2000s. And it didn't come out of the blue. Like if you read these papers and the papers by Newman and Gervin around that period, they sort of hovered a bit before zooming in on modularity. But there's this notion of connectivity and how connectivity is drive, and how the structure of a network is essentially driving the emergence of community structure. And it's very related to other notions, such as dynamic and epidemic spreading, as I quickly mentioned afterwards. So, of course, you need to define modularity as an equation, right? Because if it's a quantity that you want to optimize, then you need to define that quantity. So this is one way to formulate modularity. There's several equivalent ways of doing it. These are, and all are just rewriting of each other's. And I'm just going to introduce the different elements of that equation, and then I'll go on to a specific example to fix the ideas a little bit. So modularity is called Q for I have no idea why. And then the two elements that are really important that I mentioned here, which is the observed and expected number of edges, are encoded within the adjacency matrix A for the observed edges. So it essentially contains the information of which nodes are connected to which node, and it's a matrix. And P, which is the null model, so the expected connectivity, what sort of baseline connectivity that you would expect to observe in a null model. And I'll go, of course, now going to explain more into details what they are. And then there's the curly P, which is the partition of the network into NC communities, right? So the important thing here is that the number of communities, NC, is unconstrained. So you're not prescribing a priori how many communities you want to end up with, like you would in K-means clustering. The only thing that you say is that you want the sum. So just to understand, to unpack a bit that expression, right? So what is within brackets is essentially telling us that we're going to compare how many edges we observed between the nodes in one community against what we expected, right? And because we're in an optimization problem, we want to maximize that. And then you're going to sum that intra-community, connectivity over all communities in your partition of the network. And you want that to be maximal. So the game here is both to assign the right nodes to the right community, but also find the right number of communities. So as you can expect, it's a highly unconstrained problem. So it's so it is going to be, so I'm not spoiling any surprise by saying it is going to be NP hard, and except in very simple cases, you can never really expect to find the real minimum, but or the real maximum of the function. But as long as you have a good approximation of the truth, then you can work with something. But I'll come back to that later. So the take-home message from that slide, which is really important to take with you, is that you measure the similarity within each cluster, but you compare it with what you expect. And you want that to be maximum, right? Because you want to maximize similarity with respect to expected similarity, right? So you want to group nodes that are more similar together, if you want, than they would by chance. So now we can go back to a simple example and try to work it out. So we're going to consider the graph or the network that I presented before for the min-cut problem. And now we're going to formalize a bit what that network is and how to represent it. So the first thing is, of course, to attach an identity to each node. The identity doesn't have any, of course, importance. Like I numbered the nodes in that way, but you could randomize the identities. That wouldn't change anything. What would change, though, is once you set the identity and you randomize the identities, then, of course, that would change the structure of the network, right? So they're not equivalent nodes, but the names that you give them is irrelevant. So once you have your network, then you can start representing it as an adjacency matrix, right? So the adjacency matrix encodes the connectivity. So it tells you. So you essentially it's a 0-1 matrix, or a matrix that has 0 and 1 elements, and you have a 0 when there's no connection and a 1 when there is a connection, right? So for example, if we take node 1, then we see that node 1 is connected to node 2 and node 3, and therefore you have 1s in the corresponding columns and 0s everywhere else. And nodes are not connected to themselves, so that there's 0 in the diagonals. So you can carry on doing that for all nodes, and you end up with that similarity matrix, right? And you see really that it has a block diagonal structure, right? So you have this block here, which corresponds to the left side of the network, and that block here, which corresponds to the right side. And then you have one off-diagonal term, which is the edge, which represent the edges, the edge that connects the two blocks, right? So that's another way of thinking about clustering and community detection, is to find block structure in the adjacency matrix, right? So in this example, it's of course very simple to see it, but in general, if I had, for example, labeled the nodes differently, so 1, 2, 3, 4, 5, so then the block structure wouldn't have been apparent. But if, of course, if you were to swap columns or and rows at the same time, then by doing that iteratively, you could find again that block structure. And in a sense, that is what modularity and any clustering algorithm do, is to find block structure. And what it says at heart is that you want the connectivity within the blocks to be higher than within the blocks on the diagonal to be higher than the connectivity on the blocks that are off diagonal. then I won't define many network-based measures, but two that are crucial is the degree, which simply measures the number of neighbors a node has, and a neighbor, and you're a neighbor of a node if you're connected to a node. So for node I, you simply sum over either the column or the row. Because it's a symmetric matrix, so it doesn't matter. You sum the entries of the adjacency matrix, and that gives you the degree of a node. So you can see that for that network, nodes 1, 2, 5, 6 have all the degree of 2, and nodes 3 and 4 have a degree of 3. Sorry, that should be a 3, obviously. And another quantity that is going to be important is the total degree or the total weight on the network, right? So, which is simply the sum over all entries, and that gives you the total number of edges in the, or twice rather, the number of edges in the network, and it is used as a normalization factor, essentially. This network is, of course, very simple because it has no extra information but the topological information. But if you had weights on the edges, for example, like instead of having zeros and ones in the adjacency matrix, you would have a real number on the adjacency matrix. And you would define the degree of a node exactly the same way, and the total strength exactly in the same way. You would just sum over rows and then sum over rows and columns to get the total weight of your network. Then the key element, of course, for modularity is the null model. So it is this part here that tells you what you expect to see as connectivity between nodes. So Newman and Gervin proposed this model, so Ki Kj over 2n, which is extremely similar to the configuration model, which was a network model, so a network generation model, a random network generation model that has constraints over the degree distribution of the network. And essentially what it says is, the important bit is the Ki Kj. So remind you that Ki is the degree of a node, so that's how much connected that node is to the rest of the network. And what this essentially tells you is that by simply taking the product of the degree of nodes as a model, then you have a null model that is essentially based on homophily. So the more connected you are, the more likely you are to be connected. Right? So the larger the degree of two nodes, the larger the probability of them being connected. And if you have two nodes with very low degree, on the other hand, then the probability of being connected is smaller. So what this tells you is you're going to try to group together nodes. That it's not surprising that two nodes with a high degree are connected together. So putting them together in the same community is not necessarily going to be super beneficial compared to nodes that are not really connected, or that have a low probability of being connected, but are actually connected together. And yes. So if we compute the null model for that simple example, then we obtain the following matrix. Right. And now you see that it has a different structure of the original one, of the observed one, because you have essentially two classes of nodes. You have nodes of degree 2, which are the nodes of 1, 2, 5, 6, and a class of nodes of degree 3. Nodes 3 and 4. So naturally you have like four different types of, three different types of possibility. Like you have the probability of being connected for two nodes of the same degree when the degree is 2. The probability of being connected for two nodes, and when I say probability, it's not really a probability. The probability of nodes of the same degree but degree 3 to be connected together, and then the probability of two nodes of different degree to be connected together, right? And what we're going to do when looking at modularity and trying to optimize modularity is compare this number with this number, right? So you see that nodes 3 and 4 are the two nodes with the highest degree. So they have, by definition, the highest probability of being connected together. And you see that if you put them together in the same community, then essentially what you're going to gain is 1 minus 64, or 0.64. So that's a contribution to modularity of 0.36. But if you group together two nodes that have a lower degree, and that they actually share a connection together, like for example node 1 and 2, then the increase in modularity is like 0.72 almost, right? So it's much more beneficial to group nodes 1 and 2 together than nodes 3 and 4 together, for example, right? And similarly for node 5 and 6, it's beneficial to group them together, but grouping node 5 and 1 together is going to bring you nothing, right? Because you're only going to have a negative contribution. And so if you continue that argument iteratively here, so you say, okay, so I'm going to group node 1 and 2 together and 5 and 6 together, then what about nodes 3 and 4? Where should they go? If you put them together, then as we've seen, the increase in modularity will be marginal compared to what it could be if you put them together with nodes 2 and 3, right? For example, if you put node 3 with node 1 and 2, right? Because here you're going to have larger increase to modularity of 0.58. Because if you group node 3 with node 5 and 6, then again you're going to have a negative contribution to modularity. So in a simple example like that, it's almost easy to construct it by hand and construct it iteratively, the partition, the optimal partition of your network, right? And yes, but in general, like you can imagine, you have a network of, I don't know, tens of thousands of nodes and hundreds of thousands of edges. So it's not something you can do by hand. Neither is it something you can do manually and exhaust all the possibilities. So you end up having to use heuristics and algorithms that are going to scan for a good solution. Maybe not the optimal one, but a good one. But before we turn to these heuristics and more like sort of real-life community detection problems, I just want to give you a quick word about spectral bipartition, because spectral methods are a big class of network clustering methods. And they also underlie, to some extent, how modularity operates, because you can, as we will see later, you can make a connection between the spectral properties of your graph, or the graph representation of your network, and the community structure in your network. So we're going to look at an even more specialized problem than spectral partitioning, which is spectral bipartition. So as with the Minkov problem, we're going to want to partition the nodes in a network into two communities. So So we define the community assignment vector, which is going to be defined as a +1 if node I belongs to community 1 and -1 if nodes I belong to community 2. So it's essentially a vector of lengths that has the length of the number of nodes in your network and tells you to which community node belongs to when you have only 2 communities. And it's also trivial to verify that this quantity here is 1 when I and j belongs to the same community and 0 otherwise. So using this S formulation, this assignment vector, then you can essentially rewrite modularity as this expression, right, which essentially becomes a quadratic form. So I won't go into details, but it's a few lines of algebra, and actually, I think, yeah, Newman in his paper, in his 2006 papers, goes through some of the steps. And one thing that is important to notice is that A minus P, so the observed minus expected connectivity, which is often called the modularity matrix and written as shorthand as B, is a symmetric and real valued matrix. So you can decompose it into an eigenbasis, which means that you have a set of vectors and of eigenvectors and eigenvalues such that when you multiply that modularity matrix by a vector by that modularity matrix, then you're essentially just scaling that vector. And this has, of course, deep implications, right? Because it means, I mean, that one is not so deep because it's just algebra, but it has deep implications about how the spectral properties of the adjacency matrix, so of the network, really characterizes the community structure. Because, again, it's a few lines of algebra, but essentially, if you express the community assignment vector into the eigenbasis and decompose the modularity matrix into the eigenbasis, then you end up with that. Sorry, with that formula. And you remember that you want to maximize modularity, right? So, of course, you're going to consider the largest eigenvalue, so the leading eigenvalue. And when you remember that S itself is constrained to -1 and 1s, then you want the AI, alpha I, to be as large as possible, and that's only going to be possible when you have when you consider the leading eigenvector, right? So to enforce this constraint that the community assignment vector is constrained to -1 and 1, then you define this rule that the value of the assignment vector is going to depend on the sign of the corresponding entry. So the value for a node of the assignment of the community assignment vector is going to depend on the sign of the corresponding entry in the eigenvector. Right. So what this tells you, so this is the deep part of the result, right? So this tells you that the structure of the leading eigenvector contains the bipartition structure of your network. So if we go back to our example, then we can, the leading eigenvector of the modularity matrix is this, essentially. And by taking the sign, then you can get the community assignment. And of course, as expected, you find 2 communities, the blue community and the pink community, right? And it turns out that this is actually the maximum, the true maximum of the modularity function. One more word about the structure of the eigenvector, right? Because you see that although you clearly have two regimes of signs, which are consistent with what you expect, the loadings on the eigenvector, so the actual values of the entries of the eigenvector, are not uniform, right? There's some symmetry, so the loading for node 1, 2, and 5, 6 are the same, which is not surprising, right? Because when we were doing it by hand, by looking at the increase to modularity of grouping these nodes together, we saw that they have symmetric walls, right? And it's also easy to see that this graph is like super symmetric, not super symmetric, but has loads of symmetries. So these nodes are equivalent. It's just that they're differentiated by a sign, which tells you the sort of chirality of that graph, that induces chirality in that graph, if you want. And then the two nodes, 3 and 4, they also have symmetric walls because they have the same entries, and they again only differentiated by a sign. But what is interesting is also to look at the magnitudes of these entries, right? I mean, the magnitude somewhat corresponds to the strengths with which a node belongs to a community, right? So nodes 1, 2, and 5, and 6 are more strongly embedded in their community than nodes 3 and 4. And again, this is not really surprising because nodes 3 and 4 are actually connected together. So they link the two communities, which means that they are somewhat, they have, it's almost like, you know, like a part of them belongs to a different community, right? They have a stronger belonging to their own community, but they also somewhat share something with other communities. And this also forms the basis of centrality measures and how to analyze the structure of the communities that you find, right? So not all nodes have the same role within the community, right? So you can make a difference between roles, node 5 and node 4. Like they don't have the same role, and these are things that you can actually measure and quantify, and you can define roles to the elements in each community, which is not something you can necessarily do when you have a data set where you don't consider a network, right? Because it's only that network structure that tells you where it is. You can do it to some extent by when you look at, I don't know, for k-means clustering, and you can measure how far from the centroid of a cluster a data point is. But here you can actually quantify it and quantify the strength of the relationship of a node with respect to all the other nodes and all the other communities in the graph and in the network. Right. So I hope you're still bearing with me, and because now we're going to get serious. And sorry, Fatima, maybe we can take a quick break and see if there's a question about what we've discussed so far.
Sure, Paul. There is one early question. Sabri, PhD student here, asked, I think you answered this, but maybe you want to give a general overview. What interesting structures does a complex network have?
Sorry, what is the?
Interesting structures of a complex network, basically.
Oh, interesting structures. So so what makes a complex network actually really different from a graph is like, no, sorry, let me start again. So what is interesting in complex networks is heterogeneity, right? Because if you have something that is homogeneous, so let's say you have a network where every node is connected with the same strengths to every other node. So you have the complete graph, as it's called. Then obviously you cannot say anything if you don't have any more information about your system, right? So it's really inhomogeneities in the network. So when you start removing edges, for example, from a complete graph, that structures appears because you introduce heterogeneity in the graph. So you can compute differences between nodes at the node level. So how heterogeneous they are, for example, that's the degree distribution of a graph, right? So just to remind you, so the degree of a node is the number of its neighbors. So that's the sort of most basic way of measuring heterogeneity in a graph is by having a degree distribution that is not peaked, right? So you have a wide degree distribution. Maybe you've heard of scale-free graphs, for example, scale-free networks. You have like very particular degree distribution. And there are other metrics that you can measure at the node level that tells you how a node what a node roles is in the network, right? And while degree is a purely local measure, because it only looks at your direct neighbors, you have other measures of node centrality, as it's called, that rely on global properties of the network, like shortest path between two nodes. So shortest path is not a local property, because you need to know the graph structure in its entirety. So this is where the graph structure becomes important, right? It's because you have this heterogeneity, and to capture the heterogeneity and its impact on each node locally, you need to have global information about your system. Now, of course, it's a very strong. It's a very strong. Oh, sorry. Yes, and of course, when you start zooming out, but still looking for heterogeneity, essentially communities are a natural way of finding homogeneous regions in the graph, right? Because that's somewhat what they are, because you're grouping nodes that are similar together, and so it's a measure of local homogeneity in some sense. So community structure. So the community structure is going to reflect the mesoscopic structure of your network, and what are like mesoscopic homogeneous structure. And I think the example I'm going to show you now is going to help answer a bit, to fix a bit the ideas for that question. And of course, I say like you need global information, and it's true that in most network approach or network-based approaches, like even graph convolution neural networks, you have this requirement that you need full information about the structure of your network, but there are approximations and ways of dealing with partial information and still have some, and still gain more than you would. Gain more than if you didn't have any idea about the connectivity of the network.
Thanks, Paul. Maybe let me see if I define global and local correctly. Local is when you can just simply calculate from your neighbors. For example, degree, you can calculate locally for each node, right? So for global, you need to know information from the whole network. Then you can infer a certain value. So in this sense, the modularity is global, right?
Yes.
Okay, and maybe so if I understand correctly, heterogeneity that you mean is the individual differences between the nodes, right? And the groupings and the communities.
Yes.
Okay, so I was just not sure whether people understood what heterogeneity versus homogeneity mean in that sense. So homogeneity, a homogeneous network probably will be, for example, a complete network where everyone will be connected to everyone. So that means it's homogeneous, meaning everyone has the same number of degree, everyone has the same friends. So I think what Paul means in terms of heterogeneity here is pertaining to the structure of the network, that everyone has different degree at the very least, and different connections, and there's a different community structure.
Yes, absolutely.
That's just a comment. Yeah. And by the way, this Paul's paper is really interesting. I think it's your most highly cited paper, right? This one?
Yes, probably not for much longer because there's another one that's catching up, but yes.
Oh, I see. So yeah, people are citing Paul. So take notice of this one. This one is particularly interesting. All right, all yours, Paul.
Right. So now I'm going to give you an example of a sort of real life example. Right, so the data set here consisted of the volume, so the number of mobile phone communications between Belgian communes. So each commune here is represented by a node. The size of the node is proportional to the number of customers of that specific provider. And what is not shown here, because it would just look like a massive hairball that doesn't have any sense, is that between each node, there's a link, and that link is weighted by the number of communication between customers, between each node. Right? So it's a slight generalization of the case we've seen before, in that the adjacency matrix doesn't just tell you which communes is calling which communes, because it turns out that would be a complete network, because you have at least one customer in each commune that called a customer in every other communes. So every communes are connected. So to add heterogeneity, to make that network more interesting, then you look at the weighted, at the number of calls, not just whether there is a call. And then you discover that some communes are calling each other much more than other communes. In pairs. So now you need to optimize modularity for a larger network. It's still a small network by today's standards. Like there's about like 500 nodes, but you cannot do it by hand anymore, right? So I'm just going to give you like flashes a few slides that give you an idea about how in practice you optimize modularity, right? So as I said, it's an NP-hard problem, meaning that you're probably never going to find the real optimal solution, but you can try to find heuristics that are going to find something good enough, right? There's essentially two classes of heuristics. There's spectral partitioning that are based on ideas that I've just described, and then greedy ones, where you don't necessarily need to consider like the whole adjacency matrix at once, but you do local moves. And probably the most well-known is the Louvain optimization method. It's probably the most well-known because I think it's the one that has the most citation, but I don't think it's really the most commonly used in practice, because the main packages, and I'll come back to that at the end of the presentation, because the main packages where you can do community detection network, like in R or Python, use the Claude-Newman-Moore algorithm. So yeah, I don't know, it doesn't really matter, to be honest. But just to give you an idea of how modularity optimization works with the Louvain greedy methods, it's a local method. So it's going to look for, essentially what it does is it starts with every node in its own community, and then starts by grouping nodes pairwise by looking at which grouping increases the most modularity. So for example, if you start with node 7, then you say, okay, so how do I gain well, actually node 0 is highlighted. So do I gain more if I group node 0 with node 3, node 5, node 4, node 2, or so which pairing gives me the most increase in modularity? So let's say it's node 3. So now you start aggregating nodes around that pair of nodes, right? So you have node 0 and 3 that are together. Then you go to node 1, and then you say, okay, so node 1 is increased. So do I increase modularity most by grouping node 1 with node 2, 4, or 7? And you do that grouping. And then you go sequentially through all nodes in the network. And you do that several times. And you reach a first plateau that gives you a first modularity structure, where the nodes here, where the node assignment is of each node is identified by a color. And then you can continue more and more and more until you reach a plateau and you cannot optimize modularity anymore. There's a stochastic element in that algorithm, which is where you seed your quest, your search, sorry. So because if you start with a different node, then you might not be able to do the pairing. So if you start with node 2, with node 7, and you group node 7 with node 3, then you might not be able, then you won't be able to group node 0 with node 3 anymore in the first pass. So there's a stochasticity, which means that if you run that algorithm multiple times, you're likely to end up with slightly different solutions. But that's not the problem, right? Because you know you're never going to get the perfect solution, and what you want is a good one. And you can always measure the goodness of a partition by looking at its modularity value, right? Because that's the quantity you want to optimize. But it's also a way to explore the landscape, to the energy landscape of the modularity function. And this is really important, right? Because so modularity is a quality metric. So meaning that you can feed modularity any partition of your network. It's going to give you a value, right? So let's say you find a partition of your network. You have a partition of your network that you found using any methods. Then you can evaluate its modularity value, and that's going to give you a ranking of these methods. Like, obviously, the one that optimizes modularity should have the highest values. But the important thing here is that it's not going to tell you that this method, that modularity optimization, is a better method than Infomap or that GCN or than K-means. It only means that with respect to modularity as a definition of what is a good community structure, this is the ranking of these methods. But it doesn't mean necessarily that Infomap is not giving you a good community structure, a good and meaningful community structure, right? So it's always, so the goodness is always with respect to something. And in case of modularity, it's with respect to modularity. So, okay, so now we can go back to our mobile phone network. And we used actually the Louvain method which is fitting because Louvain is a city in Belgium. We used the Louvain method to optimize modularity on that weighted network of mobile phone communications. And what we find is this picture, right? So here again, each community is identified by a color. And what you see is that general pattern is that in each community you have like one big city or one large city and then communes attached to it, right? So a sort of basin of attraction. And indeed you see that the communities, they are spatially compact, right? So you don't have blue that is not you don't have like a blue node or a node that belongs to the blue community that is not spatially adjacent to another blue node. So you don't have nodes here in the south of Belgium, for example. You don't have blue, sorry, in the south of Belgium. So this leads to the idea that space plays a role in creating relationships. which goes back to the original question of what do we mean by expected, right? So in modularity, the null model is what is going to drive the creation of clusters, right? Because you're going to put together nodes that are more connected based, in this case, on the number of calls that they exchange, rather than any other information. And we see that if we only use that, so the number of calls between each pair of nodes in the data, then we find something that is highly dependent on space, right? So space is so the baseline for homophily is that, and we used the Newman-Girvan model, which means we used purely the topological information, so only information that is intrinsic to the network. So that can be generalized, right? Because so to measure homophily, so homophily still being the basis of how we want to measure similarity, right? So we still want to group nodes that are similar together, right? So homophily is still the general name that we're going to use for creating similarity. But instead of using a topological attribute, we could use any attribute, right? So instead of degree, and we're going to call them like n as anything. And instead of using the degree of, or the strength of a node, then you could use the number of customers, for example, of a node as a measure of its importance. Or you could use any other metric, graph metric that you can measure for that node. And then the second assumption that Newman-Girvan does is that the strength of the expected strength of interaction between two nodes is only dependent on the quantity with which by which you measure homophily, right? So it is completely homogeneous, but actually it's not necessarily true, right? You could modulate that baseline for homophily based on a third attribute, like a different attribute. So you can formulate a generalized null model by measuring homophily that using any quantity that you can measure between two nodes, and you can then modulate that strength of homophily by a potential heterogeneity in the way nodes interact. Right, so this is a sort of generalization of modularity, but you see that if you then specify that you use the degree, then Ni and j becomes Ki, Kj. And if you say that and if you specify that there's no heterogeneity, so that the nothing but the topology is going to matter for generalizing the null model, then that is essentially a constant function, like that function is constant, so there's no modulation. Then if you ensure that you normalize your model properly, then you essentially end up with a Newman-Girvan null model, so Ki, Kj over a constant. So in that sense, it's a true generalization, in that Newman-Girvan is a special case of that. So now if we try to revisit that example by taking on board this observation that space seems to be driving the creation of communities, then does distance play a role, right? So can we find heterogeneity in the way people call each other as a function of distance? So what we measure here is the weighted average number of calls, rather the average number of calls between two communes at a given distance d. So you take, for example, Brussels, and you take all the communes that are at a radius, not within, but at a radius d. Take the average, or like sum, all the calls, and normalize it by the size of the communes, right? Because, of course, if you have two large communes, whatever the distance, they're more likely to exchange calls together. So the number of calls between these two, the volume of calls between these two communes is likely to be larger, right? So if you plot that function, so the average number of calls between communes at the distance t, then you see that indeed distance has an effect, right? So it's not a constant function, it's actually a fat tail distribution. And this tells you that the further away you are, the less likely you are to call each other, right? And there's many sort of social ways of trying to explain that. For example, like you tend to call your friends, which you're going to meet. So phone calls are essentially a proxy for social interactions, like real life social interactions. You're more likely to call somebody that you're going to meet, like to fix an appointment, for example, to meet in real person. And you're more likely to meet someone that lives nearby to you than someone that lives on the other side of the country. And yes, and one thing that is like super important is that everything we do in data clustering, or 99% or 95% of what we do in clustering in general is data driven. So data is going to tell you is going at least to play a big role in telling you what is the appropriate method to use. And then within that method, what is the appropriate, for example, null model? Because had we find that there's no dependence on distance, then there's no need to go like to generalize the Newman governed null model. You would just go with it, and that'd be it. So now we can plug that null model, that Pij with that function that depends on the distance between communes into modularity and optimize it. And what we find here is that we've got essentially two big communities, a red and a blue, that I think contains more than something between like 70 and 80% of the nodes. I don't remember exactly. And then a lot of small communities that look like a bit like nodes. So clearly, factoring out or taking into account space as mechanisms that creates or that creates like communication, and the expected number of communication clearly gives a very different picture. Right? So now comes one of the big questions usually when you use these methods that are unsupervised is how do you interpret that? So the data tells you this is one way of looking at the data. But then you need to make sense of it, right? Because you could say, well, that is an interesting observation that a different null model leads to a different community structure, but can we find an explanation? And it's not always easy. Like in this case, it's super simple actually, because once you know that there's essentially two languages in Belgium, there's Flemish on the north and Walloon, or French in the south. And in Brussels, even though Brussels is in the northern part. And Belgium is a strange country, but essentially, when you show that map to a Belgian person, they immediately know, oh well, that's the two languages. So in that case, it was easy to find an interpretation because it's very natural. But in many cases, it's not so easy, right? So for example, I have a student who's looking at patient movement in hospitals between wards, and she's been doing some community detection using modularity and different null models, and interpreting the results is not easy, and she's been fighting with that quite a lot. But as I mentioned earlier, even though you might not necessarily find, even if you don't necessarily find a good interpretation for your modules, you can still take on board that this structure exists and use that as features in other models, which is what she has done, and that indeed works quite well. So yeah, interpretation is usually nice to get. It's usually good to get one, because you can sort of sanity check that the results make sense. But even if you can find one, it doesn't mean that the structure unveiled is not real and cannot be used further. And that directly leads into the question as to what is, you find a partition like a clustering, but is it meaningful? Like, is it significant? Is it statistically significant? You know that it's been built using this idea that you want significantly more connectivity than expected, but is the community structure itself statistically significant? So one way of testing for significance, which is, and it's important, is to randomize some quantity in your data and then rerun the analysis, right? Which is what we did by randomizing the weights. So changing the calls, the number of calls between communes. And you find something that is like super significant, and the same when you randomize the localization of the communes, then you also find that is significant. So the structure that is unveiled by the null model is really driven by the structure present in the data. So there is significance in that sense. Now, one thing that I realize time is passing, but one thing that I want to highlight here is that you look at the value of modularity. So modularity is normalized to be between -1 and 1, and the closer to 1 you are, the more the stronger the community structure is. Or so goes the saying, but that's actually not true, right? Because that's true for the Newman-Gervin null model, like you get a high value for modularity, but for the spatial null model, you get like a super small value, like 10 times smaller, like 1 order of magnitude smaller. But nevertheless, you've got something that is really significant, right? Like almost absurdly significant. So what this means is that it's not necessarily the value of modularity itself, but its value relative to randomization, to like modifying the structure in the system. That really matters. And indeed, what explains the fact that we have a much smaller modularity value for the spatial null model, it's that actually where the spatial null model is actually much closer, is a much better model for the structure of for communication in Belgium, right? Because it means that the difference between the observed and the expected is much smaller, because that gravity-inspired null model is closer to the reality, while just the Newman-Gervin, the purely topological null model, is actually quite far from the truth. So by getting a null model that is closer to the real data generative process, you necessarily get a lower modularity value, but it doesn't mean it's not significant. And then one last thing is, how do you tell that two partitions are different or similar, right? Because of course, when you look at these two, they are different. But I also said before that it's very unlikely that you're going to get the same partition when you use different methods. So therefore is the question, how close or how similar are two partitions? Are they just differing by a bit of noise, or are they like significantly different to each other? And sorry. And this is why it's important to always to use metrics to actually compare the community structure you get. Like, for example, in the actual data, in the randomized version of data, or between different community detection methods. And all these these metrics, like variation of information, round index, Jacquard coefficients, and so on, they are also applicable. They are applicable to any clustering that you get, right? Not just what you get using modularity or network-based community detection, but any clustering methods. You can always measure the difference between these using these metrics. So this is something to keep in mind. Now, yes, so there's one thing I want to mention more, and then I skip one and mention a last one. So this notion of resolution limit. So it's quite important actually, because what modularity does, it gives you, so you get one optimum, right? It tells you like this is a community structure with respect to a null model. This is another community structure to another null model. But it doesn't tell you anything about whether you could, for example, zoom in and find smaller communities, or you could zoom out and find bigger communities. So in other words, you are limited at looking at the community structure at one scale in your system. So to take an illustration from hierarchical clustering, it's like you have a predefined, like a built-in scale at which you're going to look at the height at which you're going to look at your tree. And you don't have a mechanism or a parameter that you can tune to change that scale, right? In hierarchical clustering, then you do it by hand, right? Because you choose, okay, I want something like very low resolution, or really high resolution, or really low resolution. But with modularity, you don't have that freedom. And this led to the resolution limit problem. I mean, not problem, but the description of what the resolution limit is and where it comes from. And it comes from the intrinsic tension of connectivity and community sizes and number of communities that is going on under the hood of modularity, and is actually a consequence of its formulation. Right. So the solution is, when you have a resolution limit, is then, of course, to include a resolution parameter, right? So Reichhardt and Bornhold, and also Arenas, which I mentioned in the next slide, essentially added one thing, one parameter to modularity, which is a gamma parameter in front of the null model. And then by scanning the value of, through the values of gamma between 0 and infinity, essentially, you are able to go up and down the scales. Because what happens is, essentially, when you have gamma equals 0, so you essentially have you have no penalization. You're not penalizing anything. You don't have a null model. So the natural minimum or optimum of modularity is to group all the nodes in one cluster. So you have one cluster. So it's like you're at the top of your hierarchical tree. And as you increase gamma, you're putting more and more weight into the penalization of your null model. When gamma equals 1, you of course recover modularity, and then when you go above 1, then you get a finer and finer resolution, because putting two nodes together gets costlier and costlier, or more difficult. Like, first you reduce the benefits to modularity, the increase in modularity, and then it becomes impossible to overcome the benefit, because the values in PI in your null model are always going to be larger than the values and the observed values, and therefore you're going to put all the nodes in your own community. The problem, it's really a sort of fix, because one of the drawbacks of that approach is that the total weight of the network is not conserved, right? Because when gamma equals 1, so in the modularity, in original modularity formulation, you have that the total weight of the network, so that 2m, is conserved, right? So if you sum over all the elements of your adjacency matrix and all the elements of your null model, they are the same. which tells you that the model is really a reorganization or a randomization with the constraints that you have to create your null model of the original weights in the network, which is something that you lose when you add that resolution parameter. But it does the job. So if you consider, for example, that toy model, that toy network, which is a hierarchical clustered network, right? So you have small clusters of 5 nodes that are then clustered together, five of them. So you have small clusters of 5 nodes. These clusters of 5 nodes are grouped together by 5, and then they are grouped together 5 again. Right? And when you, so here the R is equivalent to the gamma parameter essentially. So you're going to scan through it, and then you're going to plot the number of modules you find. So when gamma is like super small, then you get 1 module, right? So everybody is grouped together, and then as you increase gamma, then you first find this representation, right? So you find 5 modules essentially, and then you increase a bit, and then you have gamma equals 0. So that's what modularity would give you. So it's something that is different from that. It's something that is somewhere in the middle. And then as you keep increasing, then you find smaller modules, which are also an acceptable answer. Right? And then you have a fairly long plateau for that, which means it's sort of stable. And then everything breaks down, and you have everybody in their own community. There's one caveat in what they've done, though, is that they're only plotting the number of modules. And one thing they haven't checked is that the modules that you find, so the partition that you find at each value of gamma on that plateau is actually the same, right? Because it could be that for that value for this range of gamma, you find communities that have the same number of modules, but the modules are different. So the assignment of the nodes to the modules are different. But in this toy model, it's clear that it's not the case, but in real life examples, it might be a problem. And that's one of the things that the analysis of results from these multi-scale methods, like the resolution parameter method or the Markov stability methods, do in general. So in the interest of time, I'm going to skip Markov stability. It's essentially a principled way of doing the same thing as the resolution parameter, but it's a way to use the structure of the network and putting a dynamic on it, and then looking at how that dynamic evolves. And in a nutshell, the idea is to send random walkers going on in the network. Actually, I'm going to use that slide. It's easier to see. So so imagine you have somebody who starts here, and then at every time step, so you have a discrete time step, you have a continuous time formulation as well, but let's take discrete time step. At every time step, you walk at random, right? So you jump at random to one of your to one of your neighbors. Then the idea is to use that time as the resolution parameter, because when you start in a module, you're likely to stay there for a long time, right? And then eventually you're going to reach one of these nodes that are touching another community. And then once you're there, you might hop on there. And then you're going to explore that community. And then as time goes on, the random walkers are going to explore more and more of the network, right? So you're going to find larger and larger structure. And interestingly, Markov stability and modularity are connected, because modularity is essentially Markov stability at time 1. So you're essentially looking at one step random walk. So you're on your node, and where are you going to go next is what you do with modularity. So your horizon is one neighbor. While in microstability, because you have more time, then you can go further and further and further. So you have this multi-scale approach that is built in. Yes, and this, so yeah, I just wanted to just say something about microstability, because this relates to this question we had before about the local versus global structure, right? So modularity, even though it finds mesoscopic structure, very much relies on local information, while while stability and microstability is going to essentially look at the full structure of the network. So the global information is going to have an impact, but at different time scales, right? And this relates to spectral properties of the network. So modularity is essentially not the only way to do clustering of a network, right? So you have microstability, for example, which is a dynamical criterion. So it's based on the spectral properties on random walks, which are linked to the spectral properties of your network. You also have other approaches like Infomap, which is using information-based criterion, Oslam, which looks directly at the significance of clusters you find. You can also alter some of these methods, like you can alter modularity to do overlapping community detection. So, as I said at the beginning, we're looking mostly, when we think of clustering, we're thinking of hardcore clustering. So we put a node or an element of your dataset into one module. But it could be that a node could be meaningfully assigned to different modules. So for example, if you want to cluster people according to their social interactions, then everybody is going to have like a group of friends, but also a group of colleagues, a group of people they do sports with. So it can be meaningful to group nodes into separate communities. And then you have semi-supervised methods like graph convolution methods and all the spectral methods like, there's this really nice review by von Luxburg, which goes through the spectral methods, which essentially underlie modularity and microstability. Microstability, definitely; modularity, also, at least indirectly. And I just want to conclude by sort of tell you a bit like how to plan research when you want to do network clustering. So, of course, the first thing you need to come up with, even before thinking whether you're going to do clustering, is what is your research question? Is it data exploration? Do you want to reduce the dimensionality of your system by creating mesoscopic structure like data structure? And more importantly, like, is clustering actually an appropriate tool to apply? Like, because it's not because it's something that's popular that everybody does that it's necessarily going to give you useful information to answer your question from your system. Then there's the question of, do you naturally have a network? Like, is that something you can observe directly? Like, you have an intrinsic like an explicit network, like in social networks, like in Twitter or in white matter brain networks? Or can you turn your data or use part of the features of your data points to construct a network? So for example, you could have correlation matrix along built, like, computed over some, like, subset of features of your samples, and then create from that correlation matrix, threshold it or one way or another, and then create a network, and then use that in conjunction with the original features. And then what is the whole metadata that is available to you, right? Is it so do you have, if you have a network, or if you can construct a network, do you have weights, do you have direction? For example, like the intensity or the similarity between two nodes might not necessarily be symmetrical. That sounds counterintuitive, but if you think, for example, of the mobile phone network, or any communication actually between two people, you can count how many interactions they have altogether, but you can also know how many times, like, person A calls person B and vice versa, and that needs not be equal, right? And then, of course, things can be time dependent, for example. And the question is also, when you have information available, do you actually need and want to use it? Is it actually relevant? Like, for example, is directionality important in what you, in your question? Because all these three steps, or these 3 points, are going to be key in the last step, which is the implementation part, right? So if you have a super overly complicated network that is multiplex, time-dependent, weighted, and directed, for example, and I don't need to define these words so that you probably understand that there's layers of complexity that are being added on top of each other. Do you actually have access to a method that can deal with community detection on such systems? Answer might be yes, answer might be no. But then there's also the question of whether this method is implementable in your general data analysis pipeline. So is it implemented in R, in an R package, or in a Python package? Is it available as a standalone package in GitHub, for example, just given by the developer, or is that actually a fully maintained extension package like NetworkX or iGraph? And then also, sometimes you also have methods that are just described but not even implemented or not accessible. For example, like microstability was not really accessible to the outside world for like many years, despite it being an interesting method, although it has its limitation in terms of size of the system you can get. So is the method that you want to use scalable, right? I mean, modularity can be optimized for like huge networks, but not microstability, for example, because being a spectral method, it's super costly in terms of matrix decomposition. So I'm sort of going back to one of the initial slides I showed you about clustering in general, is that you're going to have this nonlinear process, which is actually reflects a lot of how research is, right? I mean, you have a network that you can create, and then you want to attach it a lot of metadata, but then you don't find the right analysis methods. Then you go back to your fundamental question, and do you actually need to use all the metadata? You have access to all the features, and so on and so forth, and then you iterate until you either conclude that you can't do what you want to do, and therefore you need to rethink your question, maybe, or your approach to your question, or you can, and hopefully that's the case. You can find the right analysis method that's going to answer the right question given the correct data and features is used. So a general summary of that talk is essentially in these 4 points, right? I mean, so network clustering has generated a lot of attention just because data availability. So a lot of data available, everybody has data, everybody has network, and a lot of data can be formulated into networks, and clustering, as I said at the beginning, is a very natural human thing to do. So we want to cluster. So a lot of people have thought about how to do it. Modularity is a very popular quality function to assess the quality of a partition of a network, because it sort of relies on an instinctively correct way or perceived correct way of defining a cluster or a module in a network. It's also NP hard, but you have really good heuristics that are widely available for all the main programming languages. So I only mentioned R and Python, but I'm pretty sure if you use Julia and other things, you might be able to find your something. And worst case, you can always try to wrap things around. But modularity is definitely not the only option, and it's not because everybody is using it that it's necessarily the best thing to do and the best thing to use. And I'm going to stop there and thank you for your attention and apologize for going a bit overboard. Thank you. And you can contact me.
Thank you very much. Okay. So maybe we can give the question poll for the participants to answer. And let me reiterate again, everyone, if you want to answer the question, please raise your hand. Yeah, there's a raise hand function there on the top. And then after that, we will answer some questions from the participant. But I think we'll give the Grab question first, just to heat up the conversation. Is it okay, Paul?
Yes, of course. So yeah, just let me. So I think the question. So it's not going to be a technical question because that. I don't think that's necessarily super fun, but it's more a general question, and I think I tried to give some elements to answer it during my talk, but is this notion of, so if you could explain or sort of try to summarize why it is important to not consider just one description of your system. So you can find a clustering, but is that a good clustering, and is that the only clustering? And why? Usually the answer is no.
Okay. Let me see if I can get that clear. Why is it important to consider more than just one type of clustering, one attribute, one?
Yes. So another way of maybe phrasing that question is, why is it likely that if you only look at one clustering of your system, you're not you're going to see, you're not going to understand 100% of the structure of your system?
Why is it likely that when you only use one type of clustering, you wouldn't understand 100% of the system?
Yes, or maybe, okay, so it's still a bit cryptic, I think. So, okay, so why in general? So I'm not talking about toy examples, but why in general? There's not a single correct answer for clustering of a system. So you find a clustering, but it's likely that it's not the only one that is valid, if you want, or that's meaningful. So why is that?
Anyone want to give their opinion? No one has volunteered so far, Paul. Why is there no single correct answer? Okay.
So, but if in the meantime, if there's other questions,
yeah, sure.
or if you have a question about the question.
Yes. So if anyone has a question about the question, they can ask or raise their hand. And in the meantime, Teddy Setiadi asks, what What is the state-of-the-art algorithm in community detection-based structured attribute modularity? I'm not sure. Maybe you can stop sharing, Paul, and read his question. Maybe I'm
Yes.
getting
Yeah.
it wrong.
Sorry. Yeah. I just. Yeah, because for some. Yes. Can you see me?
Yes, we can see you. Okay, Paul. Yeah, so Teddy Setiadi asks this state-of-the-art algorithm in community detection-based structured attributed modularity. I'm not sure if that's a specialized name that he's mentioning.
So I think it depends what you mean by state of the art, right? Do you mean, if you mean something that is scalable, fast, and reliable, in a sense, modularity is probably your best bet, right? Because I think that's one of the reasons it's so popular, is that it's super scalable. Sorry, not modularity, because modularity itself is not scalable, but the heuristics that have been developed to optimize modularity are super scalable. Like, I think in the original Louvain paper, which was 2009, maybe something like that. So some time ago, they already, like, within seconds they could optimize modularity for nodes for networks of millions of nodes. So in that sense, modularity is probably state of the art. But then there's limitations to modularity, right? So you only find one structure, essentially, right? But there might be other meaningful structure that we can find at different resolutions. So Markov stability could be said to be state of the art, because modularity is a special case of Markov stability. So when you solve Markov stability, you naturally have modularity for free as well. But because of the technical limitations of Markov stability, because it's a spectral method, then you cannot go really big, and it's really slow. So I think that's what I wanted to convey with the sort of last planning your research section, is that there's no one method that fits all, and that's going to be the answer and the best method, right? There's no perfect solution yet.
Yeah.
And there's also no single definition of what a community is, right? So because also Infomap, for example, which is an information-based community detection method, has similarities with modularity in terms of the modules they uncover. They're not necessarily really the same, and in some cases they're really different, possibly when you look at directed networks. So Infomap is much more suited for directed network rather than modularity, which needs a lot of tweaking to be able to deal with directed network. So that's why most people don't use directed network.
Yeah.
So probably if you have a very specific problem, then it's going to be easy to find what is the best method to use. But in general, there's no one shoe fits all, one size fits all. Sorry, yeah.
Okay. All right. I hope that answers your question. Teddy Setiadi, I think he's from Indonesia, Teddy. Okay, nobody has volunteered to answer the question yet. Anyone want to try to answer the question? Maybe because it's quite late actually, but we thank, okay, Teddy says thank you. We thank Paul because it's 10 a.m. I think in the UK-ish right now. Yeah, 10, 10,
11.
yeah, 10:20, yeah. So he started at 9. Okay, perhaps I think Fariha, if she's still here, she had a question about overlapping clustering to me just now. In her earlier session, she asked me about overlapping clustering. Yeah, Fariha, did she raise her hand? Yeah, she did. Okay, let's give her a chance to say something. Fariha, you can unmute yourself now.
Okay, Dr. Paul, can you hear me?
Yes.
Okay, I have a question about the TDA mapper. Are you familiar with the TDA mapper, Dr. Paul?
Sorry.
TDA mapper algorithm for topological data analysis.
Oh, map. Yes.
Mapper. Yeah.
So I'm asking Dr. Fatima a question actually. Is there any relation of the output for the TDA mapper and output from the clustering from the network? Is there any relation between the two graphs? Because the output of the TDA mapper also produce a graph actually. So it's kind of like a network shape, right?
Yes. So
And the class and the network output. Is there any relation between the network and the TDA mapper output?
so okay. So I think so that's an interesting question because so if I understand correctly, because you were breaking off a little bit. So if I try to reformulate the question, so you're asking so you have two set of methods. You have community detection that you can do on an existing network, and so you can do it and get a partition, and then you can have a pure sort of data data cloud, so a cloud of points of data, and then you apply mapper to it, and then you find at the end of the day you obtain a network, right?
Yes.
And the question is what is the so is there a relationship between the network you obtain and the type of community detection you could do on the network?
A graph TDA mapper.
So yes and no, right? So to do community detection on a network, you need a network to start with, right? So you could almost see Mapper as a way of constructing such a network,
Oh, okay.
right? And then you can do community detection on the Mapper network you obtain. But of course, there's much more information in that network that you obtain from Mapper, right? Because each node in the Mapper graph is a community in itself, right? Because it's made of samples that are connected, that are grouped together.
Yes.
So it is a community detection in itself, but it's a community detection. It's really a clustering algorithm that doesn't need a network structure to start with, right? And you're going to end up with a network. While community detection using all the methods I've talked about, you need a network to start with. But it does make sense to. So it can make sense to do community to, for example, optimize modularity on the result of Mapper, right? Because the network, the graph you obtain from Mapper does have a structure, right? And we actually did something very similar to that. No, actually, we didn't do it, but we should have done that. So we had a paper where we used a 2D mapper to group samples of gene expression. So you had sample tissues in the brain, and then so that's freely available. Actually, that's from the Human Allen Brain Atlas. So they took samples, tissue samples from dead brain, and looked at the gene expression profiles for each of these samples. And what we did was use map on a subset of genes. We used Mapper to create a map of similarities, right?
Oh.
And actually, what you find is that so you have your Mapper graph that output, and you see that they're heterogeneous, and there's almost like clusters. Like you can see that there's modules on that graph, and actually these modules correspond to different brain regions where the samples were taken. So the mapper was recapitulating a sort of anatomical representation of the where the samples were taken from. And the reason we actually didn't do community detection on that mapper was because we had the ground truth we were looking for, in a sense, because we knew where the samples had been collected in the brain, so we could give the samples a tag, and then see that the distribution of tags overlap the clusters on the mapper graph. But if we didn't had, but we could have double checked that by doing community detection, like let's say modularity detection, or community detection using modularity on the mapper graph, find the clusters, and then compare using variation of information, for example, the samples, so the clusters we found using modularity and the clusters defined by the ground truth of the original samples. So, yeah, there's no direct relationship between mapper and community detection, but you can use one on top of the other, and they both give you something. And actually, mapper is actually a good example of overlapping community detection, right? Overlapping clustering, because the nodes, the clusters, the nodes that represent the clusters, they can share samples, right? Because that's when they share samples that they're actually connected on the mapper graph.
Okay. So is my understanding correct that mapper actually, the network that Fariha gets from mapper is actually a network of clusters?
Yes.
Okay.
Yeah, because the nodes, so the nodes are clusters, right? But nothing stops you from treating them as basic nodes and do community detection of clusters. You find clusters of clusters.
Yeah.
But it's
Yes,
not a natural
Fariha.
because
It's not exactly a network of nodes, but it's a network of clusters. Fariha, do you want to try to answer Paul's question? Just give it a shot. Let me see. What can you repeat the question? Why is there no single correct answer to any particular clustering? Is that true?
yes.
Do you want to cuba je lah, just try.
Again, Dr. Fatima.
Why is there no single correct answer to any particular clustering method? I mean, any particular clustering that you can have on a data set.
Answer the question. I think that with the cluster analysis, we have actually an exploratory data analysis. So, multiple
sorry, Fariha, you are cutting in and out. Can you repeat again?
Okay.
Or maybe
maybe the line of internet is not okay right here. Okay right now?
Okay, now it's okay. Yes.
Okay. So, okay, I think that the cluster analysis is actually an exploratory data analysis. So, by applying the cluster analysis, we could have a multiple of results, right? It can be, I mean, it depends on the subject expertise. Maybe this kind of cluster that suitable for the subject expertise. Maybe in our field, the cluster result will be, the other cluster result will be more meaningful. So we cannot say that this is the exact result for the cluster method. Is it answering that question? I mean, is it clear?
Yeah, I think you're definitely on the right track, at least from what I grasped. So, yeah. So do you want somebody else to try, or should I give a bit more information?
Let me see. Does anyone else want to try? Maybe Luqman or Sabri or Syed Sadiq. In fact, for Luqman and maybe even Fariha and Sadiq, because Fariha, you asked me once, right? Because your data is spatial. Your station for the haze detection is spatially located, right, Fariha?
Yep.
Yeah, so then you can probably apply modularity from Paul's spatial modularity. If you remember his Belgium network, where he filtered out the spatial data and got something else on top of the spatial network. So this is the same case as in Lukman's case and also Sadiq's case in terms of having different station, because they are all using meteorological data, Paul. So their data is collected at particular stations in Malaysia. So I think for all these three cases, Fariha, Lukman and Zaid Sadiq, they can use your method to filter out the spatial effects of these stations being close to each other. Yeah.
Yes, and I think that's yeah.
Does anybody like Lukman or Sadiq want to comment on this? Maybe they're not here anymore. Fariha wants to comment? Yes, Fariha. No.
Okay. About the question that I answer, can Dr. If there is no one to answer that question, can Dr. Paul comment about that?
Yes, yes. So I think yes. I think you're essentially you're essentially correct. I mean, again, I don't know if there's a simple answer to that question, but I think what I've tried to convey throughout the talk is this idea that there's no single one way of looking, correct way of looking at a data set, right? Because it's intertwined with your question, right? And the data you have, and for example, I've shown that by adjusting the null model in modularity, for example, you get different answers. So you get two different meaningful clustering from the same data, right? And so there's not one that is correct and one that is wrong, right? They're both correct. And I think that's what sometimes is surprising, is that there's no single answer, right? So the two, so both community structures are correct because they're meaningful. And again, when we looked at briefly at this notion of scale and at which scale you're looking at the system, again, you might, this goes also back to this original thing about complex systems, right? I mean, you can look at the individual level. So you can consider like clusters of humans, right? So in social interactions, but you can also be interested in clusters of clusters. So not just humans, but like cities, like clustering cities together and so on. But these are all meaningful clusters that are describing the system at different scales. But not one is wrong or correct, right? So it depends on your question, it depends on the tools you're using and how you use these tools.
Yes.
So what's more important is not asking whether you can make sense or if that is the only solution you have to your problem, but is, can you assess the statistical significance of your finding? Right. So you find something, and almost from like an agnostic point of view, you're not trying to analyze it. You should just, in principle, try to see if that is statistically significant. And then if it is, then you've got a good answer, right? But it's not necessarily the only one, because if you have this multi-scale approach where you have like 3 scales that are significant, then you have 3 clusterings of the same system, of the same data point that represent different aspects of that data.
Okay. Yeah, I think that's why the randomization part at the end of your talk is very important, and I think Fariha did some similar things by comparing it with the ground truth in her data, the PM10 data. So that's very true and very important. So yes,
And actually, just to comment on that, because I think that's really important, is this notion of ground truth, right? Which is nowadays absolutely crucial in a lot of things we do, like all the convolutional neural network classification, all the like image classification, even translation and stuff. This is all based on ground truth, so on labeled data.
yeah.
Right. So I mean, it can become a bit philosophical, but what is ground truth? I mean, how are you sure that this is the correct and the best way of characterizing your system? Again, your samples, again, you don't know. You know it's with respect to one question. So the ground truth is correct only with respect to one type of, or to one question to your data, right? So is that a dog or a cat? That's only true if you're wondering like what kind of animal is on the pictures you're trying to classify. But if you're doing something else, then the notion of ground truth itself can be tricky to get, right? Because is there an ultimate ground truth for any data set? There's a research program that we're trying to do, which aims at finding emerging ground truths from the data, right? So something I briefly described at the beginning. So you do some unsupervised clustering, you find pseudo ground truth labels, and then you use them to reinforce, to then do classifications, for example. So yes, Fatima?
Yes, Paul.
Yes, no, sorry, because I saw you disappear, so I thought I was alone and talking by myself.
No. Thank you very much, Paul. It's very illuminating, but probably because it's been a long day and it's now almost 7 p.m. so everyone is tired. But I thank you so much for being here and everybody for staying in the end to the end and having questions. And this is the end for WCNTDA 2021. Please help us make it better by filling in the feedback form I put in the chat, and you can criticize and say how bad it was or how good it was, but how we can make it better. And perhaps the next time we can have you really here and physically, hopefully. Thank you very much for joining us. And if you have any questions, let me know. I will email everyone the videos and the slides. Paul, please email me the slides afterwards so that you can refer to this talk again and again. Till next time, take care. Assalamualaikum and thank you.
Thank you very much.
Thank you. Bye.
Bye.